under the properties, let us take the next property, that is some nucleophilic additions also takes place. The reason for the nucleophilic, generally alkenes will not undergo this type of the addition, only alkynes undergoing. The reason is again the acetylene carbon is sp hybridized, therefore 50% s character, more electronegativity. So, the electron cloud will be the carbons hold tightly. So, attacking electrophile, that is electrophilic addition reaction slightly decreases. To that extent, some nucleophilic addition reactions also we are observing. Only one or two examples are there. One is with HCN, hydrogen cyanide adds to alkynes in nucleophilic addition pattern. So, H plus and the cyanide minus. So, it seems the cyanide minus first attacks, H plus second attacks. So, first cyanide minus attacks either side, you can show this way or that way. So, cyanide is added one side and H plus is added other side. So, cyanide will be, so still double bond will be there. So, you will have a CH2 and H. This is called vinyl cyanide, vinyl cyanide. Also has a common name called acrylonitrile, acrylonitrile, common name acrylonitrile. This compounds on polymerization, just like vinyl chloride will give say polyvinyl chloride, acrylonitrile will give a unpolymerization polyacrylic products. Now, this acetylene, so 1 H plus, it is studied that cyanide minus first attacks followed by the H plus. This is the second step. So, that is why it is called a nucleophilic addition reaction. But if somebody argues why not H plus attacks first, if H plus attacks also, the same answer will come. Why don't you consider as a electrophilic addition? That is valid question. But this was studied by, if a small quantity of barium cyanide is added, the addition of barium cyanide working as a catalyst. How this catalyst is working means this cyanide first attacks, it seems. Huge amount of cyanide ions will be there in the medium. Now, the cyanide will attack first, followed by the H plus. That means, in the step 1 cyanide is there. So, that is the rate determining step. In the rate determining step, the cyanide is involved and the cyanide concentration increases, rate is increasing. So, therefore, it is come to understanding that cyanide minus is the attacking species. That is why nucleophilic addition reaction. Similarly, we have one more addition with methanol or some alcohols like ROH. You can take acetylene and add the methanol. Methanol has got a way of splitting into H plus and the methoxy anion, or the whole methanol will be added, later H plus is deleted. Even this is also we can argue why not first H plus, but this also we have a support that instead of only methanol, if a sodium salt of methoxide, sodium methoxide, if it is added to the medium, this works as a catalyst and this methoxy will be the attacking species initially, and after this methanol addition the H adds and methoxy is reimbursed to this the catalyst. So, this methoxy comes into the compound, this methoxy goes into the reagent. So, that is why again this is proved that this is a nucleophilic addition reaction. Either side, because identical, either side you can add. So, still double bond will be there, CH2. This is called a one side vinyl, one side methyl. So, we call methyl vinyl ether, vinyl methyl ether. So, two one side vinyl, one side methyl ether. That is common name. However, if you want to name it, you call it as a methoxy group containing ethene. Methoxy ethene. That will be the systematic name. Here, the carbon is included into the chain 1, 2, 3. Propene nitrile. Propene nitrile. Ene is there, so propene nitrile will be the systematic name. So both these compounds have got the industrial application. Their polymers are having the very good application in the industry. So that's why the acetylenes are converted into their polymers, and then that is monomers, and thereby polymerides are prepared. Then let's go for the next reaction, that is alkyne shows some special property, that is acidity and metal derivative formation. Metal derivative formation. As I said already initially when you are introducing, alkanes are neutral, alkenes are basic. Alkynes are expected to be more basic but less basic because the electron cloud is attached to the carbon. But however, whenever the acetylenic carbon holds one hydrogen, this breaks heterolytically and liberates a proton plus this acetylide anion. So this proton giving, this is called as a proton donor. Therefore, proton donors are defined as acids. So that's why the acetylene is behaving like an acid. So it however, it is very weak acid. If it is really acidic, enough acidic, it would have react with KOH. So it won't react with bicarbonates and even sodium hydroxide, potassium hydroxide, but with some metals it is reacting, showing some slight acidity or the reactive hydrogen presence it shows. So such reactions we can claim here. The first one with a sodium metal. So acetylene reacts with the sodium metal. Thereby we can prove that the acetylene is acidic. This sodium will have a one unpaired electron, that is in the valency shell, one extra electron is there. So that electron would like to donate easily. That's why the sodium is a very good reducing agent. It's an electron donor. In this case, you get a H plus sign minus. The H plus will take electron, forms into the H dot. So this gives one electron and forms into H dot. Two such H dots will join, you will get the hydrogen gas. So in this reaction, we are going to expect the hydrogen gas. This hydrogen gas is not by combination of the two H pluses. H plus cannot react. So H plus will receive one electron from the sodium, which is given from the sodium, will become into H dot and join to give the H2. So what about this acetylene? Similarly, even this side also one proton. So two sodiums are used, two hydrogen join this one. So both the sides you will get the sodium. So Na plus, C minus and C minus with Na plus. So it is a disodium acetylide. Disodium acetylide, which is a solid actually. A solid substance is formed, but the hydrogen is liberated as a hydrogen gas. So the sodium is base here, acetylene is acid, a salt, and the hydrogen is liberated. So it is a neutralization reaction, acid base reaction, acid and the base salt is formed, right. Similarly with a sodamide, NaNH2 also it reacts. Acetylene reacts with the sodamide, NaNH2. Now in this H plus is undergoing reduction also in the first case. See. So the sodium is losing electron, H plus is undergoing reduction. So it is a redox reaction actually, but in the second case there is a H plus is there, minus already this you can break it, plus minus is there. no one is going to change its oxidation number or the charges. Na plus is there, afterwards also you have the Na plus only. So, you will get the monosodium or disodium salts of acetylene depending upon the minus and the Na plus. Sodium, monosodium salt, ammonia is formed, that is liberated as a ammonia gas. So, in this reaction H plus and NH2 minus acid, this is a totally 100% neutralization reaction. A base and acid gives a salt and a solvent, isn't it? A salt is formed, ammonia or water, some solvent is formed, that is liberated as a gas. If excess of sodamide is added, some book says the other side also reacts and you will get the disodium acetylide and you will get. Both these salts we have used in the application of the converting the lower alkynes into higher alkynes. If disodium salt is treated with methyl chloride, both the sides methyl will come, it is converted into the 2-butyne. If this is treated with methyl chloride, one side methyl will come, that is propyne can be prepared. So, ethyne can be converted into propyne, ethine can be converted into 2-butyne and so on. So, these methyl derivatives have one crucial role or importance role in the preparation of higher alkynes from the lower alkynes. Provided the acetylenic hydrogen is there, that hydrogen you can make into a salt and then add one R. So, different types of the alkyl groups can be introduced on the acetylenic carbon. However, if the triple bond is in the center, for example 2-butyne, now 2-butyne you cannot extend to become. If 1-butyne is there, terminal hydrogen is there, you can make a sodium salt, add Rx, you will get the alkyl group. So, the hydrogen attached to sp carbon only shows acidic, that is why they react with the sodium, otherwise all compounds will not, all alkynes will not react, only one alkynes or terminal alkynes only will react. There are two more reactions which is also on the same principle, acidity forming the metal derivatives, that is with a Tollens reagent. Tollens reagent. The Tollens reagent is nothing but a ammonium hydroxide and the silver nitrate mixture. So, it is also called as what? Ammonical silver nitrate, wherein silver will be in the complex form, Ag plus attached with the ammonia molecules internally. So, Ag plus is going to react with this one here. Anyhow, it is a neutralization here. So, therefore, acetylene reacts with ammonium hydroxide. Skeleton reaction is here, the plus of that reacting with the OH of this one forming into water. It is a neutralization, ammonium hydroxide OH and this one. However, in the place of the H plus, it's not NH4 plus, but the silver is going to come. So, we are going to get a silver salt, both the sides reactions takes place. So, you have to take 2 silver nitrate. So, therefore, you will get the twice the reaction, both the sides silver is coming. This is called disilver acetylide, disilver acetylide, which is a having a white color as well as it is a precipitate. So, therefore, whenever in a reaction, organic reaction, if a compound becomes into precipitate, you have one application called quantitative application. The precipitate you can filter it and dry it, take the weight of compound, divide it by molecular weight. So, weight by molecular weight will give the moles. So, how many moles of silver acetylide is formed we can? If somebody gives a mixture of acetylene gas and ethane gas mixed, so many ml of gas is mixture of gas is given, from that how many grams of or how many moles of silver acetylide is formed? Rest of moles will be the definitely will be the ethane gas. So, you can go for such type of the estimations. Similar the way, if a two different flasks containing the one acetylene, the other one ethylene, only acetylene will give this white color. The color is a qualitative analysis, that is whether it gives color or not. Yes, acetylene gives, ethylene won't give, ethane won't give. So, 3 gases, 3 different jars. How do you say the one which is acetylene means the one which gives white color with adding this tolerance reagent is known as what? Acetylene, right. The tolerance reagent is an unstable mixture it is. So, you have to prepare the and there you take silver nitrate, add 1 or 2 drops of sodium hydroxide, you will get a silver oxide mud color precipitate. Go on, add ammonium hydroxide till the precipitate dissolves, then add 1 or 2 drops extra. That ammonical silver nitrate solution is called tolerance reagent. So, you can add this and subsequently what happens this. So, silvers are substituted and the H and the OH forms into water, plus you have a ammonium plus nitrate, ammonium nitrate is formed. So, you have 2 silvers are required, so 2 nitrates, so 2 ammonium nitrate, so 2 ammonium hydroxide, 2 OHs and 2 Hs, 2 waters are formed. This is a balanced equation here. Similar the case with the another reaction with ammonical copper chloride. This reagent has no name, but ammonium hydroxide plus copper chloride Cu2Cl2, a mixture of cuprous chloride and the ammonium hydroxide. This is called ammonical copper chloride solution. When this is added also the same type of the reaction, ammonium hydroxide OH minus and the H plus is the main reaction, that is water formation, neutralization. This is acid, this is base. But in the place of hydrogen, the cuprous salts are coming. So, Cu2Cl2, it is a dimer, CuCl is the formula, but doubled compound dimer we are taking, and anyhow 2 Cus are required. So, you take 2 ammonium hydroxide, so that the 2 Hs and 2 OHs forms water. So, the main product will be the copper substituted acetylene, that is dicopper acetylide or cuprous acetylide, Cu2C2 is formed, which is also a very good catalyst for the several other reactions. Now, the ammonium and the chloride forms ammonium chloride plus H2O is formed. So, 2 OHs, 2 water molecules, 2 chlorines, 2 ammonia, 2 ammonium hydroxide. So, this is again a precipitate which is having the red color and precipitate. Because precipitate we can go for the quantitative estimation, because the red color is there, qualitative identification of acetylene and ethylene gases, differentiation or acetyl, the distinguishing tests between alkynes and alkenes. You too can differentiate 1-butene from the 2-butene. 1-butene will have a acidic hydrogen, therefore, both the C and D reactions will be effective. The C reaction gives the white precipitate and the D reaction will give the red precipitate with this replacement of the hydrogen, whereas 2-butene has no reaction. So, one can go for the differentiation of 2-butene from 1-butene because this hydrogen. So, it is not that all alkynes, you cannot say as a blanket rule that all alkynes are going to react with the tolerance reagent, that is wrong. Only the alkynes which have one of the end hydrogen, this is called what? One alkyne, can be a 1 propyne, 1 ethyne, nothing but the ethyne only, 1 propyne, 1 butane, 1 pentyne, like that. So, the terminal alkynes are 1 alkynes are the alkynes which one side the hydrogen containing, all alkynes are going to react with the sodium metal, sodamide, and with this tolerance reagent and this one. Even you can have one more reaction, that is with the Grignard reagent. Acetylene also react with the Grignard reagent, we have seen in the extension or the, that is conversion reactions. The R and the H forms into alkane, a gas is liberated. So, acetylene becomes into the magnesium derivative. These are all called metal derivatives. Metal derivative means one of the metal atom like copper, silver, sodium, magnesium coming into the alkynes, you can term as a metal derivatives. All these metal derivatives, as we have seen, when you add a Rx, beautifully the R comes into the alkynes. So, therefore, we can have a R substituted alkynes. So, extension of the alkyne into the higher alkynes, ascending the series you can prepare. So, this especially the C and D have got a quantitative and qualitative approach also, because the derivatives are solids, precipitates are coming, and the color also white and the red color. Therefore, they enable us to use as them to as a differentiating or distinguishing reagent. Especially we have a name tolerance reagent, which is also used in the aldehydes ketones differentiation. It is a mild oxidizing agent. So, therefore, in that case aldehydes are oxidized with this reagent, ketones are not. So, therefore, aldehydes ketones can be differentiated using this tolerance reagent. In the carbonyl chapter we take up this again tolerance reagent. So, let us have one more property of the alkynes is the sixth property. This is also a very good reaction. This is an addition of alkynes on carbonyl compounds. Now, the reaction is slightly in a other way. It is so far what we have seen is different reagents we are adding on the double bond or the triple bond of the alkenes and alkynes, that is addition reactions we say. Alkenes undergo electrophilic addition. Even alkynes also undergo electrophilic addition twice because two pi bonds are there. So, HX will be added, another HX, because first time one pi bond, second time another pi bond is opened and reagents are added this side, that side. But here this case is different. The alkynes we cut into AB and then add it on the carbonyl compounds, this type, that is addition of alkynes on the carbonyl compounds. Carbonyl compounds will have a C double bond O. When I add a E plus and N minus, their characteristic reaction is first N minus is added, that is called nucleophilic addition reaction as a characteristic reaction, because this opens into plus minus where plus is very reactive or less stable. First nucleophile will add. It is not the greatness of the nucleophile, but the positive charge formed on the carbon is highly or more reactive than the negative charge formed on the oxygen. So, therefore, first nucleophile will be added, followed by the electrophile. So, carbonyl compounds have one characteristic reaction. Most important reaction of the carbonyl compounds is nucleophilic addition reaction. Variety of reagents we have, but in this case we are adding, instead of electrophile, nucleophile. The example is here as a acetylene we add it, breaking the proton and the rest of acetylide anion. So, let us take one example. We take formaldehyde, then add acetylene. So, acetylene break up into the minus and the plus. Okay, this acetylene bond we cut into minus and plus heterolytically, and the plus is added, minus is added. Now, according to that reaction, first acetylide is added, right, on the carbon. So, this opens into minus and plus, on the plus the minus is added, the H plus is added on the minus as a second step. First step happens to be a nucleophile. Therefore, for the carbonyl compound it is a nucleophilic addition, not with reference to the alkene. Alkyne is the reagent in this case we are adding, and this reaction is catalyzed by the copper acetylide, that is CuC2, nothing but an acetylene with the both the sides copper. So, copper acetylide is the catalyst here. In the presence of copper acetylide, the acetylene adds. That means actually maybe the minus of this one will participating in the reaction. Later acetylene converts into the copper salt. So, what happens is now to this carbon the acetylene is added, and this carbon will have 2 hydrogens. This O will become OH. So, let me write this other side of the OH. So, this O will become OH, the entire acetylene is added. So, like this. Even the other side also reaction takes place. Once again reaction takes place. One more acetyl the formaldehyde you take and add it. The carbon is added, hydrogen is added. So, you will get a acetylene with the right side 1 CH2OH, even the left side 1 CH2OH. That means acetylene will add on the 2 formaldehydes this side and that side. The first time you got a propyne with all, second time butane with diol is formed. Both have got some commercial application. One of the application, let us see on this particular the reaction. This compound, when you treat it with hydrogen and nickel, so the OH will not be reactive toward this reagent, but the triple bond will become single bond. So, CH2, the carbon will become CH2, that carbon also will become CH2 and CH2OH. This is nothing but the butane 1,4-butane diol. A diol is formed, but 2 OHs are there on the 1 and 4th carbon, therefore, you have to mention this 1,4-butane diol. This compound on subsequent reaction with the I2 and phosphorus, you can convert into the iodide. So, both the OHs are iodide, convert into iodide. Then later you treat it with the potassium cyanide, both the iodides are converted into the cyanides. So, this is called a hexane dinitrile. This side nitrile, that side. So, hexane dinitrile. This hexane dinitrile is taken up and converted into 2 different products. One side you hydrolyze it. When you hydrolyze, cyanide group is hydrolyzed to become into the acid. So, this side acid will come, even the other side also you will get another carboxylic acid, liberating both the nitrogens in the form of ammonia. Other side what you do is you add hydrogen nickel. So, it is a triple bond. So, therefore, what happens? It will be undergoing a reduction of hydrogen, 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 hydrogen. So, you will get a already 4 CH2s are there, one more CH2 with NH2 is formed. This side also you will get 1 CH2 and the NH2. So, this is nothing but the 6 carbon hexane with diamine, 1,6 diaminohexane or hexane diamine is formed. This is hexane dioic acid. In the dioic acid we have a series called 2 carbon dioic acid, oxalic acid, malonic acid, succinic acid, glutaric. This is adipic acid. So, it is called a adipic acid, which is a common name. Adipic acid is a common name, just like oxalic, malonic. These are all series of common names. Now, this is called in the similar way adiponitrile and adipine diamine, the same name may be extended. This adipic acid and this adipine diamine is mixed together and polymerized in presence of the acidic medium. This is a polymerization step. When you polymerize, now what happens? The 6 carbon acid, 6 carbon diamine go on joining, a long chain is formed which will have the CH2 will have 6 times, now 4 times, one CO will be there and another CO is there. Now, this CH2s will be there with NH, CH2 6 times NH. Now, this unit will be N times. This is our dicarboxylic acid, this is our diamine. A dicarboxylic acid is adipic acid, diamine hexane is used. So, dioic acid is used. This compound is called nylon 6,6. What is this 6 stands means 6 carbons of the dioic acid, 6 carbons in the diamine. This is 6 CH2s are there. 4 CH2 plus 2 carbons. So 6 again. So 6 6. So it is called nylon 6 6. So once again let me see how this compound is formed. Formaldehyde is added to acetylene. So one side addition took place and propionol is formed. The reaction is continued. You will get both the sides you will get hydroxy methyl groups are coming. Methylylation or hydroxy methyl groups are coming both the side. This is nothing but the butane diol. The ion is reduced with hydrogen nickel so that a 4-member dihydroxy compound. The hydroxy is converted to iodide and then cyanide. The cyanide to dioic acid and diamine separately. Half the product that side, half the product this side is converted. Then joined and polymerized. Very good industrially useful. Nylon is a polymer. Nylon is a polymer. What is the monomer of this polymer means? We have 2 monomers, it is not one. Generally polymers will be one monomer, go on joining, you will get polymer. But in this case it is 2 different monomers are there, one after the one, A, B, like that. One dioic acid, one diamine, then again dioic acid will come like this, one acid, one amine. Now acid will come, amine, acid, amine, like that. A long chain of polymer is formed. Such polymers are nothing but the nylons. They have a amide as a functional group. What is the functional group in the polymer called nylon means CONH. Obviously CONH is an amide bond, but in proteins we find as a peptide bond. So all our organs of our body is mostly by the proteins constructed. So this nylon is very eco-friendly, one of the popular polymer, very useful in different the industrial applications. That is called nylon 6,6. This is the one application of this carbonyl compound we have taken as a formaldehyde and then acetylene. Similarly, we have another application. Now let us take one more similar type of the reaction. Instead of formaldehyde, you take the acetone now. Is another example, good example of a ketone is now acetone are systematically called propanone, commonly known as acetone, or 2 methyls with ketone, dimethyl ketone. That compound also undergo beautifully the addition of acetylene in presence of copper acetylide. It will split up into plus minus. So the plus is added on the O, the rest of the minus part is added on the carbon. However, first nucleophile will be added, that is the nucleophilic addition reaction of carbonyl compound. So the minus part is added here, followed by the plus. So the O will become OH. Let me write now 1 methyl. Okay, the O I will write as a OH, another methyl, right. Then continuation of this acetylene. Okay. Now you may call it as a 1,2 hydroxy 1 butane containing 2 methyl, 2 hydroxy, that is 2 methyl 2 but 3 ine 2 ol. Slightly difficult to name. 2 methyl you have to say first. Okay, this is the extra group, and this is called a but ine is on the third. So 3 ine 2 ol, butyne ol it is actually. From here we have named so that ol gets a preference. So 1, 2. Good example for the nomenclature application. 2 methyl but 3 ine 2 ol. You cannot shift the 3 ine 2 in front because 2 are both are significant numbers, keep it there only. So this compound now you have one industrial application. This compound you treat it with the Lindlar's catalyst, that is adding hydrogen in presence of a specific catalyst called Lindlar's catalyst. Lindlar's catalyst allow the addition of hydrogen only 1 mole, that is palladium supported by the barium sulfate in presence of an organic solvent called quinoline. With this the triple bond is reduced, however, but only up to the double bond. So, you will get a double bond here, CH double bond CH2. Now, this is named as again 2-methyl bute 3-ene-2-ol. This is, instead of ine we have a ene here, that is all. Now, this compound is a dehydrated minus of H2O. For dehydration we can use a classical reagent, that is concentrated H2SO4 at 170 degrees centigrade, or alumina at 350 degrees also works for the dehydration. So, which H will go means this identical, that side H accumulated. So, therefore, 1 H from this side, 1 H from that side, that is OH from the other side will be eliminated. So, OH and the H both removed as a water. So, double bond will come. So, we have already a double bond that side. This side also you will get 1 double bond. This type of 2 double bonds alternatively is known as a conjugated dienes having 1 methyl. Now, let me write the methyl on the top, okay, just shifted. Now, this is nothing but the 2-methyl 1,3 butadiene. This is commonly known as isoprene. Isoprene is a well known compound which is a monomer for the natural rubber. So, therefore, this isoprene when you polymerize it, you will get a long chain polymer having the double bond in the center. At this double bond level, if the compound is a cis type of compound, this will be the nothing but a natural rubber. The polymerization should be controlled using a specific catalyst like Ziegler-Natta catalyst, so that only cis form is formed. Only cis polymer is having elastic property known as natural rubber, but this is no more a natural. This is by totally we are synthesizing outside the plant, isn't it? It's a synthetically we have prepared an equivalent to this natural rubber. Natural rubber is a product extracted from the plant, actually called a rubber plant or Hevea brasiliensis, but here we have prepared it totally synthetically this rubber. So, acetone adds to this acetone. On acetone, acetylene is added, and then it is the triple bond is reduced selectively to double bond. Then another double bond is generated by dehydration. Then it will become a butadiene having a 2-methyl is commonly known as isoprene. The isoprene on polymerization gives polyisoprene R, which is nothing but the natural rubber. However, the polymerization is a totally stereochemistry controlled polymerization. If you do, you will get rubber, otherwise a hard substance where there is no cis type of double bonds are not present may be also formed. So, you control the polymerization so that this natural rubber is formed. Both the previous example, that is nylon preparation and the natural rubber preparation, both are there in the IIT syllabus specifically as a polymers in the polymers topic. Natural rubber and the nylon both are there as a for the study of this preparation and properties. So, this covers that particular part also. From the alkynes we are able to prepare this the rubber natural rubber.